having listened to that introduction, nothing I'm going to say now is as complicated as that whole story about how I ended up here. But I just thought I'd say where Haverford is, because it's no shame in never having heard of this place. It's in this part of the developing world, and it's just outside Philadelphia. And there's a local connection. Haverford was founded by the Quakers, who left England in 1833, but not all of them left, because there's a nice place to eat lunch here, which is the Quaker house. Okay, so I just thought I'd say a few words about quantum computing in 2015. Perhaps redundant for this audience. So the first thing to say is, when someone asks you a technological question, when will we have flying cars, when will we have a quantum computer, if your reflexive tendency is to say, oh, about 10 years, because it sounds like a long time, well, there are many people in the field who've been saying that for 10 years now. However, it's not all bad news. There's lots of nice experimental progress. So in my opinion, there's a nice pathway and a nice view to how to scale up things, at least in superconductors, optics, and ions, if there's nice pathways to other implementations. I don't have them on here just because of my own ignorance. There's lots of industrial interest, especially in the last year. D-Wave, Peter already mentioned, have been around for a while. But also Microsoft are now heavily active. Google have a group. Intel are interested in doing various things. So for students, there's lots of potential jobs in places that pay more than universities do. And there's nice applications in machine learning, quantum simulation, specifically quantum chemistry, which I worry about a lot. There's adiabatic quantum optimization, which we can do, but we don't know if it's useful. And cryptanalysis, which of course is where the field started, but with Shor's algorithm for breaking RSA cryptography. So of course the only applications of Shor's algorithm are espionage, terrorism, and crime. So it's nice that we have more socially useful things to do with a quantum machine. So what the motivation of the talk today is that all of these applications are based on a small and slowly growing set of algorithmic techniques. When I started working on quantum information in 2002, it was sufficiently close to Shor's algorithm that I think I and a number of people had this very naive belief that there would just be a lot of quantum algorithms. And if you just went looking for them, you just stumble over them like someone in California during the gold rush or something. And that turned out not to be true. So any new techniques are good, and so looking at problems that are going to teach you new techniques is a worthwhile thing to do. So I just wanted to say a few words about quantum chemistry. This is a picture of S.F. Boys at Cambridge in about 1950 after the war, and this is the EDSAC machine, which is a sort of immediate descendant of the machines that Turing and various other people were building during the war. And this is his 1950 paper where he's calculating the ground state energy of the beryllium atom on this machine. This is, by the way, about a 3-qubit calculation in 1950. So if you look now in one of the small number of well-used quantum chemistry packages, you might read something like this. This is a restriction gains the total number of blah, blah, blah. This is just the size of the problem. In practice, you will probably run out of CPU time or disk storage long before you reach this limit. So this is just saying that these are very difficult problems. So in 2005, Alan Asper-Guzik and I wrote a paper where we said, well, hey, these are quantum systems. We know quantum computers can be used to simulate other quantum systems. And so let's think about the use of these techniques to solve these problems that Boys started doing in the 50s. It's very funny, by the way, if you read this literature, particularly Boys' paper from the 50s through to the 60s, they're at the point where vacuum tubes get replaced by transistors. The papers start having very excited words in the introduction. It says, with the advent of high-speed digital computers, the replacing the vacuum tube was a big deal. Okay, so there's lots of recent work, and by recent I mean the last 18 months. So if you just want to Google Asper-Guzik, Poulin, that's David Poulin, Nathan Weeb at Microsoft, Matthias Troyer, who is everywhere, and Sabrakais and Jiří Pitner in the Czech Republic. There's lots of interesting papers. So the basic takeaway message about what the difficulty of quantum chemistry is you have this large fixed precision overhead. So chemists care about precision in their answers more than almost anything else, and that's because for anything to happen in chemistry, there has to be a change in energy, and so you have a small change in energy on a large background. So the way to think about that precision limit is like wanting to know the mass of a ship to the mass of the hat of the captain of the ship. So, roughly speaking, these algorithms are cheap in qubits but expensive in gates. So we are agonizing and agonizing to reduce the gate counts. We're going to have a workshop in London on the 11th and 12th of March, so watch this space, there'll be more information about that soon. There's some local UCLQ folks, Gauss Toliwai, who's away today, unfortunately, and Andrew, who's here in the audience, who are working on this, so if you'd like to talk to them about it. So I would say that mostly these methods rely on well-established techniques, and the problem's large fixed precision. So variety in life is a good thing. So today I want to talk about a problem with a very small precision requirement, and the goal of working on this problem was to try and discover some new techniques. So now to change gear totally, I want to talk about Moebius, something called Moebius Inversion, which I'm reasonably certain nobody's heard of in the audience. And I just want to give a physical motivation. So imagine a one-dimensional solid with a lattice spacing x, has an interatomic pair potential, like the Morse potential here, with maybe, so here's three versions of three different spring constants. So there's a problem. How does the energy of an individual atom in the chain depend on the separation x? So that's something I can measure. And of course, for an infinite chain, it's just the sum of this distance. It's the sum of the interaction of me with my neighbour, then my second neighbour, my third neighbour, my fourth neighbour, all the way out, because this could potentially be a long-range interaction. So here's the sum over all spacings. So I can measure E and I want to find V. That's an inversion problem. So I can think about this as being the sum of an infinite number of applications of this translation operator, where the translation operator acts on V of x to give me V of nx. And the goal is to invert this horrible infinite series. Okay, so as Peter said, my degree is in physics, so I'm now going to do a whole bunch of horrible things with infinite series that may or may not converge. They do converge, okay? So I'm not going to worry too much about convergence, but they do converge. Okay, so how do we go about constructing this inversion? Well, we can use a property of this translation operator, which is if I act with T, with a translation by A, followed by a translation by B, that's the same as a translation by A times B. And I can use the fundamental theorem of arithmetic, which is that every integer n has a unique factorization into prime numbers. So I have a prime p1 raised to some power, prime p2 raised to some power, and so on and so forth. So now let's just write down a few terms. So T15, T16, T17, T18. Well, that's T3 times 5 is 15. 2 to the power 4 is 16. 17 is a prime number. 9 times 2 is 18, so that's 3 squared. T3 squared times T2, and so on and so forth. So I can construct this series in a different way, which is I could take all the powers of the translation by 2, which is a prime, all the powers of translation by 3, which is a prime, all the powers of translation by 5, which is a prime, and multiply together these infinite series. So how do these terms come from this series? Well, okay, I have 1 times 3 times 5. That gives me this term. I have 4 powers of T2 times 1 times 1. That gives me that term. I have I have T2 times 2 powers of T3. That gives me that term. And so on and so on and so on. So I can make every integer by having every power of every prime. That's what the fundamental theorem of arithmetic says. And so I can rewrite my sum like this. I just take the prime factorization of each n, and then I reorder the terms. So I have a product of series. So I have a product of series where each series is a sum of powers of a prime translation.
Can I ask you a quick question?
Yeah.
How do you know it's okay to reorder the sum? Isn't that sometimes problematic with infinite sum?
Since it might not converge.
Yeah.
It converges.
Okay.
So the reason this converges is because is for a physical reason, right? Which is that your interatomic potential must get weaker.
Okay.
If you did this for a Hookean potential, one that doesn't get weaker, then the series wouldn't converge and none of this would be true. But as I said, I don't want to get too much. I don't want to get bogged down into series conversion. So notice that this here is a geometric series, which we know an expression for. And so I can invert this operator, which is now just a product of things, by making it a product of the inverses of these summations. So this is 1 over 1 minus TP. So the inverse of that is 1 minus TP. So I have a product over things that I know how to invert. So now I've basically done my inversion. I can write my interatomic potential in terms of my measured energy in the following way. But that's still not quite what I want. So I want to write this in terms of a sum of shifts with some coefficients. And I can figure out what the coefficients are if I look at this product. So firstly, each p in the product appears exactly once. Okay? So there's no numbers n here which have repeated primes. So n has to be of the form a product of unique primes. So that means that this coefficient, mu of n, is 0 if that isn't true. Okay? Now, I have P1, P2, P blah, 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 blah. Now there's a minus sign in front of my shift. So if I have an odd number of primes, I pick up a minus 1. If I have an even number of primes, I have no minus 1. So I have minus 1 to the number of primes. Okay? So this mu is the Moebius function. And I'm transliterating my German here, so I don't have umlauts. Okay, so I'm just writing OE. You can have an umlaut if you want, but it's incredibly tiresome to make umlauts in a talk, and B, makes everything look like a heavy metal album. Okay, so that was Moebius inversion. So you can think of this as arising from, the problem, this nice physical problem of getting the interatomic potential from an energy function you could actually measure, and the prime factorization of the integer shows up in a nice way. So there's two definitions. This is the one that I've given you. So I have any g that's a sum of translations of any f, and then I can invert like this, and there's a condition for convergence that I'm not telling you. But I can also write it in the following way. If I have a g that's defined as a function of n, such that d is a sum over the divisors of n, of some other function, then I can invert it in the following way, and the Moebius function appears again. So now there's some number theory notation I have to bring in. So d vertical line n means d divides n. Okay? So 2 vertical line 6 is true, because 2 divides 6, and so on and so forth. So I'm not going to explain this definition, but this is a sum over a finite number of things. So if you were worried about convergence in this, you can stop worrying about convergence. Okay? But I don't have a physical motivation for this version of conversion. Okay, so if you want to know about more applications of Moebius inversion, there's this nice book. Notice on the cover, there's a Moebius strip. There's nothing to do with the two, no connection between those two ideas except Moebius stores them. But I suppose if you're a publisher, you have to put something on the cover. You can't put 1 minus 1, 1 minus 1, 0, 0. So one nice application of this is you could actually use this to try and invert black body radiation. If you have a distribution of black body radiation where you've got two populations at different temperatures, you can actually use this to get out the distribution of temperatures. So there are actually papers in astrophysics where people have actually done this and used this method. This is, for maybe some people from the CCS have heard of superstatistics, but this is an application of this. I don't think this connection's been made in the literature, but it's fairly obvious. Superstatistics is where you have a distribution of an intensive parameter, like temperature, and then as a result you get some different effective distribution. And so you can use Moebius inversion to pull out the distribution of the intensive parameter. And this is sort of was my entry point to this topic. Was a friend of mine wrote a paper showing that the Moebius function is something called the Witten index for a system called the prime gas. So that is obscurity squared. But the Witten index tells you the difference between the number of fermions and the number of bosons in the ground state of a supersymmetric system. So it tells you whether supersymmetry is broken or unbroken. So that's something you care about enormously if you think about supersymmetry, because supersymmetry is either untrue or broken. And the prime gas is a really strange free quantum field theory where you have excitations that correspond to the prime numbers. So this is the kind of thing that's completely bonkers, but it makes a nice connection between number theory and physics in some sense, because the numbers I was writing down before, which have unique primes, correspond to occupation numbers that are either 0 or 1, so they're fermionic. If you have powers of primes, you have occupation numbers that are greater than 1, so that's the bosonic set. Okay. So it's slightly obscure, but in any case, this was my original interest. So the interest was, okay, I think about quantum simulation. This is a quantum system. It's a free field theory. It should be easy to simulate. Can we calculate the Moebius function by simulating this free field theory? So then you have to face a lot of horribly complicated issues if you want to start thinking about simulating supersymmetric systems and blah, 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 blah. So then that led into the question of, okay, can you just, never mind the quantum simulation aspect, is there a simple quantum algorithm for the Moebius function? Okay, so there's another way into thinking about the problems of Moebius inversion. So as a society, we've made a huge bet that factoring is hard, because we all rely on RSA cryptography almost every day. But there's no theorem that factoring an integer, i.e. obtaining that the powers and the primes that appear in that expansion event, there's no theorem that says that's hard. So in Alexei Kitaev's book on quantum computing has the brilliant phrase, because we don't know how to prove any of this, but these things are believed by wide circles of narrow experts. So this is another thing that's believed by wide circles of narrow experts. So I was driving from Benasque in Spain down to Barcelona with Andrew White, and we ended up, for some reason, having a conversation about this. And Andrew was saying, well, do you know of anyone serious who thinks factoring could be easy? And the answer to that question, it actually turned out to be yes, I do know someone. But I just want to make the point, if factoring is easy, of course computing the Moebius function is easy. Because if I show you the prime factorization, you count the prime factors, check there are no powers. You have to decide if a number is odd or even, but I assume you can do that. And so there's another question, which is the Moebius function itself hard to compute? So if easiness of factoring would imply easiness of Moebius, easiness of Moebius would not imply the easiness of factoring, but it's perhaps an easier question. So Peter Sarnak has some nice notes and lectures on his website. Peter's at the Institute for Advanced Study, and he doesn't believe factoring is hard, he believes factoring is in P. And Peter Sarnak and I had a nice conversation where he found out I worked on quantum information. He said, I'm a huge fan of quantum information, because he thinks the existence of Shor's algorithm is evidence that factoring is classically easy. Because we have one polynomial time algorithm and one model of computation, right? So that shows that for some devices it's easy, so why wouldn't it be easy? Now I'm pretty sure that he's being deliberately provocative when he says that, but nevertheless, if you don't know who Peter Sarnak is, you might know who Andrew Wiles is. He's the guy who proved Fermat's last theorem. So Peter Sarnak inherited Andrew Wiles' job at Princeton when Andrew Wiles was back in the UK. So these are extremely serious numbers.
So you're saying it might be easier to prove a negative answer to the question, is the Moebius function hard?
Right. So can you prove anything about the complexity of the Moebius function? It would be of interest, because if you could find an easy classical algorithm for the Moebius function, maybe you could actually do that. And you have to remember, there are serious consequences to finding an efficient classical algorithm for factoring, right? Because it breaks out of it. So you could find an efficient algorithm for the Moebius function without breaking the law.
Right. But it's probably harder to prove the Moebius function is hard.
Oh, yeah. Or equally difficult. So one thing about the Moebius function is if you do an individual evaluation, you get a result that looks like an increment in the random walk. It's either +1, -1, or 0. So it's interesting to look at the sum of all those increments. And indeed, it does look like a random walk. Except if you evaluate this again, you get the same answer, of course. Because although it looks totally random, all the steps are totally determined by the integers. So it's a very interesting thing to think about how random is this. And this is actually Sarnak's program. So if this was truly like a random walk, this object would be bounded by constants above and below. Okay? So if you scale it by the root of the number of steps, you expect this thing to be bounded. In fact, so this looks totally plausible, right? It's the kind of thing mathematically you play around with it. You can convince yourself this is probably true by just doing a ton of examples. But actually proving this is equivalent to proving the Riemann hypothesis. That's likely to be somewhat tricky. So you want to look for a more tractable definition of randomness or easiness. And so the program that Peter Sarnak proposed was to find function h such that the inner product, if you like, of h with the Moebius function converges to something constant as n goes off to infinity. So the correlation of the function h with n, with the Moebius function, doesn't just vanish as you look at larger and larger things. So h is a function in some sense that tells you some information about the Moebius function. So we started off thinking about factoring. Computing the Moebius function is easier than factoring, probably. Now we're trying to make things easier still by saying, well, we don't really want to calculate the Moebius function. We just want to find some function that has something to do with the Moebius function. And h, if you just set h is the square root of n, then that's equivalent to proving the Riemann hypothesis, so that's probably not a good place to start. So this, it turns out, is a simple enough question that some things are already known about. So these are in some sense the simplest things you would want to prove, but it's nice that they've been proved. So h is not in AC0, which is the set of polynomial size circuits with constant depth. And h is not monotone. So a monotone function, or a monotone circuit, if you like, is a circuit that has no NOT gates in it. Okay? So these are the kinds of things we know how to prove about lower bounds. Okay? So lots of things are known to not be in AC0. Like parity. Computing the parity of a bunch of bits is not in AC0. So this is, I think, just an indication that that people are interested in this and are working on it. So this is a function or an area where we're likely to know more in the future. This is an area where we're likely to know something about the lower bounds of computing the Moebius function. And if someone can show that it's not in P, then that would be very interesting. Okay. So let's think about this from the point of view of quantum computing. So it's obvious that this is in BQ. Right? This is something that you can compute with a quantum computer simply because we know Shor's algorithm exists. So you find the prime factorization, and from there you can just calculate the thing with a pencil. So the question for this talk is there a direct quantum algorithm? Is there an algorithm we can use to calculate the Moebius function without ever writing down the prime factorization as an intermediate step? From the fact I'm standing here, you might assume the answer to that question is yes. But there's an initial step, which is you can calculate whether it was already known when I started doing this work that you could calculate whether the Moebius function was 0 or not 0. In other words, this algorithm by Lee determines the square-free decomposition of an integer, particularly determines whether it's square-free or not. And those square-free integers are exactly the integers where the Moebius function is either 0, is either -1 or 1. Okay? So this is an algorithm for computing when the Moebius function is 0. Okay, at this point I need to tell you about some number theory, so I can explain how the algorithm works. So I just want to start with the most elementary operation, which is just do two numbers share a common factor. So we know finding the factors of a number is hard, but whether two numbers share a common factor is easy. In fact, it's possibly the oldest algorithm and the oldest application of complexity theory is the Euclidean algorithm, which is about 300 BC. So how does it work? Well, for two numbers where x is greater than y, you just write down a sequence of remainders, and you keep going until there's no more remainders. And the final remainder is the greatest common divisor of the two numbers. So what does that look like for an example? So 15 is greater than 6. So 15 is 2 times 6 plus 3. 6 is 2 times 3. So the GCD of 15 and 6 is 3, which happens to be the right answer. So something else I assume you will know, but let's just say it out loud. So modular arithmetic is, in the previous slide we were using remainders. Modular arithmetic is just the arithmetic of remainders. So if I take 0, 1, 2, 3, mod 3, I check away all multiples of 3, and I just get 0, 1, 2. So let's take the first interesting question about modular arithmetic, which is when is a number a square mod n? So if I take these numbers mod 6, I have 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, so on and so forth. So 10, for example, is 4 mod 6, and 4 is 2 squared. So 10 is a square mod 6. So that means 10 is what's called a quadratic residue mod 6. If it's not a quadratic residue, any normal person would think it was a non-quadratic residue, but for reasons beyond understanding, it's called a quadratic non-residue. So the answer to this question was figured out by Gauss, so I can tell you my favourite joke, which is, what's the most famous father-son team in mathematics? There have been quite a few, so Cartan, the two Cartans, a bunch of Pancares, they're not Pancares, who are they? Bernoullis. So the answer is, so who's the most famous father-son team is Gauss and whoever his father was. So, how do we sort out this question? There's a nice definition here of the Legendre symbol, which tells you if something is a quadratic residue. It's 1 if it's a quadratic residue, minus 1 if it's a quadratic non-residue, and it's 0 if it's 0 mod p. Okay? So, what if for p prime? So what if I have an n that's not prime? Then I use the Jacobi symbol, which is a product of Legendre symbols. And by the way, any sensible person again would think this is n divided by p. You're just supposed to know. Okay? There's no way of discriminating this from division. It's just supposed to be obvious from the context. And it's remarkable that although this is defined in terms of the prime factor, factorization, this symbol can be computed efficiently classically. In fact, it's quadratic in the number of bits of n without reference to the prime factorization. So you don't have to compute the prime factorization of n to achieve this little information. So we can calculate when two numbers have a common factor. So what's the probability, what's the probability two numbers don't share a common factor? So what's the probability that the GCD of x and n is 1, i.e. that they're relatively prime to each other, they have no common factors? And the answer is the number of numbers like this, less than n, less than or equal to n, but with no common factors, is the Euler phi function. And the probability is bounded like this. Here's the Euler phi function for the first 200 numbers. So you can see it goes from 1, and it appears numerically to be bounded below. And in fact, it is bounded below by this thing, e to the gamma. Gamma's this thing called the Euler-Mascheroni constant, but it's, for all intents and purposes, a half. So this is like the square root of e times log log n. So there's this nice lower bound here. And this lower bound is saturated for an infinite number of integers. So it's not a useless, too low lower bound. So this fact is something we're going to use repeatedly. And in fact, this also shows up in Shor's algorithm as a success probability. Sorry, just need one more thing, which is the multiplicative group mod n. So that's the set of residues, or the set of integers mod n, such that GCD of x and n is 1. So here's an example for n equals 20. None of these integers here share a common factor with 20, 21, 22, 30 here. So you can just see that if you just write down all the numbers that are relatively prime to an integer, that's called the multiplicative group mod n. It's an abelian group under multiplication because the product of any pair of these mod n also has no common factor with n because neither of them has a common factor with n. And the order of this group, i.e. the number of elements in it, is just given by this Euler rotation function I just wrote down. Okay. So with all that, we can start talking about square-freeness. How does the algorithm for square-freeness work? So we have to define something called a Gauss sum. So this is a sum of m of this Jacobi symbol from 0 to n times this phase. And this thing, remember, so these sums have a really nice dichotomous property, which is that this sum is 0 for every value of y, such that the greatest common divisor of y and n is greater than 1, only if n is square-free. Okay? And it's 0 if the GCD is equal to 1 if n is not square-free. Okay? So these sums actually help you distinguish cases where n is square-free from n is not square-free. And so this is the basis of the quantum algorithm of Leopold for square-freeness. You basically construct states where these Gauss sums are the amplitudes, and then you have something you can measure that can discriminate square-freeness from square fullness. Okay, so in our algorithm and in theirs, there's a nice ingredient which is called the GCD state. So the GCD is efficiently classically computable. I just told you that by the Euler algorithm, by the Euclidean algorithm. So therefore, I can define this transformation. Sorry, this B should be up in the superscript. So I have an ancilla state with B bits, an X and an N, and I write the greatest common divisor of X and N into the ancilla. And if we can efficiently generate a uniform superposition over n elements, which is a nice exercise to work out how to do it, combining these two operations gives us the state, which is the uniform superposition state over all x, tensored in each case with the GCD of x and n. So how do we prepare this? So here's a circuit. We compute the uniform superposition over n elements. I'm feeding n in, by the way, as an argument here. You could equally well just write down the circuit separately for each n. Then I compute my unitary, which calculates the GCD. This is just a classical reversible circuit that calculates the greatest common divisor. And then I get this state here, which has a 1 if and only if GCD is 1, and then has a bunch of other values. Okay? So if I measure this ancilla state and I see 1, then I've prepared the superposition over only those integers such that GCD of x and n is 1. So it's a superposition, if you like, over the multiplicative group modulo n. Okay? And this is all using standard tricks in quantum circuits. So how do I do square-freeness on top of that? So here, the Jacobi symbol is also efficiently classically computable, so I can write down the classical circuit that computes that. So I can also do a phase kickback where I multiply this state by plus or minus 1. Then I get the following state, which is called a chi state, which is the GCD state just with the value of the Jacobi symbol written in front of it. So it's plus or minus 1. It's like the GCD state with a bunch of phases in front. Then I can take the Fourier transform of that. You know, I'm sorry, I was expecting a bigger screen. So I'm sorry, it's probably a little bit small. So here, this is the Fourier transform. So if I Fourier transform my GCD, my chi state here, I end up with a state whose amplitudes are Gauss sums. Okay? And remember, the Gauss sum has this dichotomous property. So if I then, on top of that, again calculate the GCD, I have a state whose amplitudes are Gauss sums, and then the GCD of one of the two arguments of the Gauss sum. So this coefficient here, this state, which I call disk for discriminate, is this state if n is square-free, and it's this state if n is not square-free, where this number here is always greater than 1. So I measure my ancilla and I see a 1, I know that n is square-free. If I see anything other than 1, I don't know. I know that it's not square-free. Okay, it doesn't matter what this value is. If it's not 1, then it's not square-free. So this is a slight variation on what Lee did, because they wanted to actually construct the square-free decomposition, so they wanted to know what the square part was. I don't care what the square part is, because I don't need that information. Okay, but this lets me discriminate using just these tricks, square-free from non-square-free. So now I just have to concentrate on, when I know the Moebius function is non-zero, how do I calculate it? So now to do this, I have to come up with a better formula, a more useful formula for the Moebius function. So now I can actually use my multiplicative group mod n, and I can write down some nice one-dimensional representations of this thing, which are just the primitive roots of unity. So there's the primitive roots for 5 through 14 written down in the complex plane. See, now with unlaps, this really would look like a heavy metal album. So what do you, this is a bit of audience participation here. What do you notice about these pictures? Can you see them? So if you stare at the pictures, what leaps off the...
Symmetry.
Sure.
Consecutive pairs of primes.
So, but what were you going to say?
Yeah, like.
So Gary's comment is that so this is clearly symmetric. This is clearly symmetric. In fact, you notice that if you sum up the primitive roots here and here, you obviously get 0. Right? So then the other thing is, they all have symmetry about reflection in the x-axis, but some of them seem to be more pointy this way, and some of them seem to be more pointy this way. So if I actually write down the sum of the primitive roots, then it's 0 for this one, it's 0 for this one by inspection. It turns out it's 0 for this one, although it's harder to see by eye. But everywhere else, it's either plus or minus 1. Okay, so the sum of these primitive roots is minus 1, the sum of these two is plus 1, these is minus 1. And if I look and think about what the value of the Moebius function is on these numbers, well, 5 is a prime, so that's 1 prime and 1 is odd, so that Moebius function is minus 1. 6 is the product of 2 distinct primes, So the Moebius function is plus 1. 7's prime, it's minus 1. 8 is 4 squared times 2, so, sorry, 2 squared times 2. So 0 here. 9 is 3 squared, it's 0 here, and on and on and on. So that gives us a very nice feeling that maybe we can... Oops, sorry. This is a little over-animated. That there's probably an expression for the Moebius function in terms of the sums of primitive roots. And perhaps I won't go into too much detail about this given the time. But this is another example of Moebius inversion. So you can write the sum of all the roots of unity as a sum of the primitive roots times the divisors of n, and a sum, over the divisors of n. So here's an example for n equals 6. Here's all the roots. And so here you can also see the definition of a root is not primitive. It's where you get a cancellation in the exponent. So then what you end up, if you do those cancellations, you get a bunch of things in the denominators here. And so if I order them, so here's 2 is a divisor of 6, 1 is a divisor of 6, 3 is a divisor of 6, and 6 is a divisor of 6. That's my sum over the divisors. And then I have my sum over the things where the GCD of A and D is 1. And that accounts for everything in the sum. And this is generically true. But this formula has exactly the form that we know we can apply Moebius inversion to. So it's this form. It's a sum of a function over the divisors of n. And I can invert that to get the function of n, again a sum over the divisors, times the Moebius function, times the function I want to invert. So here, this is my function f of d. It's the sum of primitive roots. Here's just turning the handle. And then I get this. I get more or less what I want. Here's my Moebius function. But I get this nasty mess here. However, we know that this thing is 0 unless c is 1. Okay? So this is a sum, if you like, of it's a sum of the elements of the representation of the group, the one-dimensional representation of the group. So it's the inner product of a non-trivial representation with the trivial representation. And so the inner product is 0 unless this is the trivial representation. So this proves what we had just observed with those small number of examples, that mu is just given, mu of n is just given by the sum of the primitive roots of unity. And this is a good expression because it looks quantum-y, right? It's a sum of phases. It's the kind of thing you could imagine showing up in a quantum mechanics calculation.
Got about 10 minutes.
Okay. So now, it's actually slightly better to define a generalized version of this, where I stick a y in there. So I have a sum of x e to the 2 pi I x y over n. And this is nice because if GCD of y and n, this extra parameter that I threw in there, if that's 1, then y is an element of the group. Okay? So the things that appear in the exponent here are elements of the group, the multiplicative group mod n. If I multiply each element by a fixed element, it just permutes the elements of the group. It just permutes the terms in the sum. So, of course, the sum itself doesn't change. If you just change the order of summation, nothing changes. So this thing is equal to mu of n if this GCD conditions holds, and it's equal to this funny, horrible thing if otherwise. So now this is good because it doesn't just look quantum-y, it looks Fourier transform-y. So now we know how to do it. So if we just take the Fourier transform of the GCD state, we get a state whose amplitudes are given by the values of this function mu y. So we can split that sum up into terms where the GCD of y and n is 1, and terms where it's greater than 1. They added autocorrect, which autocorrects ancilla to ankle. So maybe that'll catch on. So we add an ankle, and in the ankle, we compute the GCD again. So in this huge number of terms, we get 1, and here we just get whatever other GCD. So again, we can apply our favorite trick, which is you just measure the ancilla. You see it's 1 with this probability phi of n over n, which you have a nice lower bound for. And if you do that, then you obtain mu of n times the GCD state. Okay, so you've multiplied the state you put in, which is the GCD state, by a phase, which is just the value of the Moebius function, which, remember, we know is either plus or minus 1. Okay. So if we can do that, we can do it as a controlled operation, which means we can use phase estimation to obtain the phase. So if I just add yet another ancilla and use it to control whether or not I compute the Moebius function, whether or not I apply the phase, and then I take a Hadamard transform of my ancilla, then my ancilla ends up having T mod 2, which is the parity of the number of prime numbers in n, which is exactly the information I need to calculate the Moebius function. So we're done. And we've done this all you need is the preparation of the GCD state, which is quadratic by naive methods. We need a Fourier transform, we need yet another GCD, and a Hadamard, 2 Hadamards. So it's pretty straightforward. It's much, much more straightforward than running Shor's algorithm enough times to get the complete prime factorization and then computing it with a pencil. Okay, so there is a good efficient quantum algorithm for the Moebius function. So we can get this without using Shor's algorithm as an intermediate step, which was the goal. The naive cost of this is quadratic. Everything here, if you just use the simplest method you know to make a uniform superposition state, to calculate the GCD, to calculate Jacobi transforms, to do the Fourier transform, all those things are quadratic in the number of bits of n. That's why it's efficient. You can improve on all of those things, but they all suffer from a kind of interesting phenomenon, which is the use of the Schoenhaag-Strassen algorithm for multiplication, which is a Fourier transform algorithm for multiplication. If you have a small integer, the most efficient thing to do is the thing you learned in primary school. But this becomes like n log n for truly, truly huge integers. And so you can use this to make it almost linear asymptotically. The only reason that I'm kind of down on this asymptotic scaling is that you really know where that asymptotic threshold is. But nonetheless, from a complexity theory point of view, this is this can be made almost linear, i.e., number of bits times some logarithmic factor. So Shor can be made log depth. There's an architecture for this given, or polylog depth given here. But it's actually a really interesting question to ask: how do you make the computation or the quantum computation of the GCD log depth? So that question is discussed here. So that's, if you're a student and you want to think about something related to this, that's a nice thing, I think, to think about. And of course, calculating the Moebius function is a sort of precursor step to doing the Moebius transform. It's interesting to think whether the Moebius transform can be a new useful primitive for quantum algorithms, just in the way that calculating the Fourier transform led to a lot of things dependent on the Fourier transform. If we can do Moebius inversion, compute Moebius transforms, maybe there are other things we can do with those. Okay, so this reminds me to thank the NSF and bizarrely the United States Air Force and UCLQ for funding. Thank you.